Section 6.4 is the Gram-Schmidt process. So up to now, we've been dealing with orthogonal bases and orthonormal bases, and we've seen that they have useful characteristics that help us decompose vectors in terms of their orthogonal projection onto a subspace plus a vector that's perpendicular to a given subspace. Now, the question remains as to how we might generate an orthogonal basis for a given subspace if we don't already have one, yet we do have a basis for that space. So that's what the Gram-Schmidt process does. It allows us to take a basis for a subspace and convert it into an orthogonal basis to that subspace. So let's start with a couple examples before we actually jump into the actual Gram-Schmidt process and result. So these examples should motivate more or less how this process works, and kind of show that it essentially does work. It'll give us the intuition before we actually see the theorem. So if we have a space W that's equal to the span of two vectors U1 and U2, where U1 is this vector and U2 is this vector, note that these vectors are not orthogonal to each other. So we have 3, 6, 0, and 1, 2, 2. 3 times 1 is 3, plus 6 times 2 is 12, is 15, plus 0 is 15, which is not 0. So these vectors are not orthogonal. They are linearly independent because neither is a multiple of the other. It looks like the first two entries would be off by a factor of 3, but the third entry is different by a factor of 0. So they're certainly not linearly dependent. So the idea is to do this. We have two vectors. We know how to find the orthogonal component, or the component of U2 that's orthogonal to U1. And that's probably going to be what we need to do in order to come up with an orthogonal basis. So remember that if we decompose U2 as a vector U2 hat plus Z here, where U2 hat is parallel to U1, or in the space that in the space spanned by U1, and Z is orthogonal to this vector U1, or the space spanned by this vector, then well, we don't really need this component in our vector U2. We just need this component Z, because after all, this U2 hat is just alpha, just some scalar times U1. So it doesn't add anything new to the space that we're trying to generate. So all we need is the orthogonal component of U2 in order to generate the same thing that we would generate with U1 and U2, only in two orthogonal vectors. So really the first thing we can do before we even consider that is just say, well, let's just let U1 be our first vector in the basis. So there's no other vector in the basis right now, so there's nothing to be orthogonal to. So our first vector is essentially for free. So our first vector in our orthogonal basis will be 3, 6, 0. Now, then we'll extract the component of U2 that's orthogonal to U1, and since the other component, U2 hat, as explained before, is parallel to U1, we can just throw that component away. We don't include it as part of our basis because we want only the part of U2 that's perpendicular to U1, right? Anything else, the other component that's parallel to U1 doesn't give us any new information, so we just throw it away or leave it out of our basis. So what we're really looking for is Z in this decomposition, and we'll couple that with our first vector U1, and we'll have an orthogonal basis for this space W that's spanned by U1 and U2. So we do the usual amount of work, right? We find U2 hat. It's the projection of U2 onto U1, and the formula for that is as it was before. U2 dotted with U1 over U1 inner product with U1, all times the vector U1. And what we get out of that is this 15 over 45 scalar times the vector 3, 6, 0. Remember again, that's our U1 vector. And that's 1/3 times 3, 6, 0. We get 1, 2, 0. And that's U2 hat. This is the component of the vector U2 that's parallel to U1. And observe, it's redundant information as far as a span is concerned, right? Or as far as a basis is concerned. 1, 2, 0 is just a scalar multiple of 3, 6, 0. So we can extract or subtract that out of our vector U2 to get the orthogonal component of U2 to U1, Z, and that'll be the vector that we really want. So we basically subtract the information of U1 here, right? Our U2 hat vector from U2 to get this orthogonal component Z of the vector U2. It's orthogonal to U1. Now, we could call it done here and say that these are our two orthogonal vectors in our basis, right? 3, 6, 0 and 0, 0, 2 would make up an orthogonal basis for W. We could see that almost directly by linear combination of things to see that these two vectors are a linear combination, or as a linear combination can form this vector or this vector as we choose, right? In other words, we can form, well, generating this vector is pretty straightforward, but we could divide this vector by 2 and then add it to this vector and we generate U2. So we see that we have the same spanning set here. Now, they ask for an orthonormal basis for W. If they just asked for an orthogonal basis, we could stop with these two vectors in our list. But for an orthonormal basis, remember that our vectors have to be not only orthogonal, but also unit vectors. So we normalize Z by dividing it by its magnitude. Well, the magnitude of Z is 2. We do 0 squared plus 0 squared plus 2 squared, square root of that. So that's square root of 4 to get 2. And well, essentially we just divide the vector 0, 0, 2 by 2, and we get this unit vector. Similarly, we find the norm of U1, which is 1 over root 45. And then we divide all the entries of U1 by 1 over root 45. When we're done simplifying, we have this vector right here. So our basis, our orthonormal basis in this case, is given by B here in the bottom corner. Okay, so it's fairly easy to check that the basis vectors that we pick are orthogonal to each other by taking their inner products. That's one check we can have. And when we only have two vectors to begin with in our basis, we're looking for two vectors that we'll end with in our basis, and we could just check that we could check that they're linearly independent. Well, if they're orthogonal, they are linearly independent. And as I argued before, you could see that the span of these two vectors is equal to the span of these two vectors. And the way we know that is, I already talked about multiplying. It was easier when we were dealing with these two multiples of these vectors, but the linear combination of these two vectors that generates this vector. We can see that we can easily generate U2 from our given basis, and we know that we'll then span the same space. So, and we know that these vectors here, or that originally these two vectors, are in the span of these two, because all what they were built by were linear combinations of vectors. So alpha U1, right? And then Z was U2 minus U2 hat. Remember, that's alpha U1. Z is a linear combination of the vector U1 and U2, our original basis vectors. So we know that the vectors in this set are in the span of the vectors of these two vectors as well. So their spans will be equal to each other. Now this will extend to more than two vectors, more than bases with more than two vectors in them. It might be a little bit harder to see that, but at heart, what's happening is that anytime we build a new vector, it's a linear combination of vectors that were previously in the set, right? So we know that the new vectors we build here are in the span of our original set, spanning set, and vice versa. We could really just solve for this U2 vector here to see that it's a linear combination of vectors that were also previously in that set. So that one's a little bit harder to see, but I might try to argue that a little bit when we look at the Gram-Schmidt theorem. So let's do another example with more than two vectors. So we have these three vectors in R4, U1 through U3 here. They're linearly independent, obviously. If you put them into a matrix and put it into row echelon form, you'd have 3 pivot positions, which would match the number of vectors, or each column would have a pivot position in it. It's another way to think about it. They ask us to construct an orthogonal basis for W. Okay, so again, first one's free, right? U1, that's going to be our first orthogonal basis element. There's nothing to be orthogonal to when the set's empty, so we just add our first vector to it. Now we repeat what we did last time. For our vector U2, we're going to find the orthogonal projection of U2 onto U1. That's the part of U2 that's parallel with U1, or in the space spanned by U1. And we're going to throw that out of U2. We're going to subtract it out of U2 and keep only the component of U2 that's orthogonal to U1. In other words, we're looking for Z again. In this case, since we're going to do this 2 times, we're going to call this Z Z1. So we decompose the vector U2 as its component parallel to U1, or in the space spanned by U1, plus its component that's perpendicular to the space spanned by U1. And then we're going to replace U2 with Z1, with this orthogonal vector. So to do that, we need to find U2 hat, which is alpha times U1, and that's just the projection of U2 onto U1. And remember, that's U1 dot U2 over U1 dot U1 times U1, and this is the result of that. And now to find Z, we subtract from U2, we subtract this vector alpha U1, or U2 hat, or this projection here. And when we do that, that's this vector minus this vector, and we get the result that we see over here. So this is our second vector in our orthogonal basis. Now remember, just to argue that this is going to work both ways, this vector Z that we built is a linear combination of U2 and U1. So it means that it's in the span of these 3 vectors still. So we know that where the span of any vector in the set that we're building is in the span of these vectors, and vice versa, to see that any one of these vectors is in the span of these vectors is to note first that, well, U1's already been included automatically, and then Z1 is just a linear combination of U2 and U1. And if we were to solve for U2, we'd see that we could generate U2 as a linear combination Z1, a vector that's in our new basis, plus this projection, which is a linear, a scalar multiple of U1. So it tells us that any vector, that our vector U2 is in the span of our 2 new vectors. Okay, so that's a lot of hand waving. The book does a nice job of explaining this in the Gram-Schmidt proof of the theorem. So maybe you can have a look at that there as well. So just, it's a bit of hand waving, but just to justify that, rationalize that the spans of each consecutive vector that we add to this, U1 and U2 will span the same space as, let's see, Z1 here and U1 that we're already picking, right? So there's U1 and Z1 are now the 2 complementing vectors to these 2, or corresponding vectors to vectors U1 and U2. So far, this is our list of basis elements. Okay, so with 2 vectors in our basis, they form a subspace, right? So the span of these 2 vectors form a subspace, and in fact, it's a plane. Actually, 2 vectors forms a plane in Rn, and we'll call that subspace S. And what we'd like now is to find a 3rd vector, Z2. It's going to be based off this vector U3 that we haven't used from the original basis. And we want to find the component of U3 that's perpendicular to our space S, or orthogonal to our space S. Okay, so that just entails a slightly bigger formula, right? So Z2 is the component of U3 orthogonal to S. Well, we've done that. We've decomposed a vector U3 as a component that is in the space S and orthogonal to the space S. We did that in the previous section. So now what we need to do then is we're going to take U3 minus its projection onto the space S. So we need to calculate U3's projection onto the space S. And remember that that now involves two vectors, right? The first standard basis vector we added to our orthogonal basis, and the second basis vector that we added to our orthogonal basis. And remember, this is U3.U1 over U1.U1. U1's the vector here. And then we've got U3.Z1 over Z1.Z1 times the vector here, Z1. So, and what we arrive at out of this is the following. We have, well, this arithmetic to simplify, we end up with 0, 2/3, 2/3, 2/3. So that's our projection of U3 onto the subspace S. Now, in order to find the orthogonal vector to this subspace S, we need to subtract from U3 that projection. Now, again, I want to stress that this is U3 combined with a linear combination of vectors that we've already shown to be in the span of U1, U2, and U3. So we know that Z2 is going to be in the span of U1, U2, and U3. And for a similar argument going the other direction, we know that the vector U3 is in the span of this vector, and then Z2 once we find it. So we know that we're still spanning the same space as we work through this, and we're coming up with an orthogonal vector to the subspace S. So that difference looks like the following. We have U3 minus this projection vector that we came up with. And what we get out of that is this column right here. And of course, that is our third vector to add to this set. It's our third and final vector because we're matching the number of vectors in our original set. So this is our orthogonal basis for W. Notice that these vectors were not orthogonal to begin with. The inner product of U1 and U2 is not 0, so it's not an orthogonal set, nor is U1 and U3 or U2 and U3 for that matter. But all we need is one failure to not have an orthogonal basis. And down here, though, if we were to check the pairwise inner products of each of these vectors, we would find that, yes, they are in fact orthogonal to one another. So not only that, but they span the same spaces. So this leads us to the general result for the Gram-Schmidt process. This could be repeated beyond 2 or 3 times and p times for a given basis of x1 through xp in the space Rn, right? So again, just as we did before, the first one's free. So we just pick the first vector on our basis and we just set our new basis vector v1 to be equal to that first basis vector. And then we go through the process of subtracting the projection of x2, right? We pick up x2 and we get rid of its projection onto v1 or onto x1, right? What's more important is that we get rid of its projection onto v1 because as the subsequent steps come, well, that this is actually critical. And this is a place where a student might make a mistake. So you want to keep an eye on that situation. Now, again, as noted before, V2 is a linear combination of x2 and, well, V1 is x1. So it's a linear combination of x1 and x2. So V2 is in the span of x1, x2 from up here. And then a little bit harder to argue, at least to see here, x2 is in the span of V1 and V2. Maybe we could see that here reasonably well by realizing that V1 is x1. So this is an x1, and then, well, V2 is equal to, oh, okay, so we'd have to solve for x2. X2 is equal to V1, a linear scalar multiple of V1, plus this vector V2. And we'd see that, yeah, okay, so x2 is in the span of V1 and V2 as well. So in return, it's also, the x2 is in that new spanning set of the vectors V1 and V2. Now, when we just had one vector, this V1 equals x1, this means that the span of V1 equals the span of x1. That's obvious. So that's the base case really to consider. But what I've sketched here for V2 really just continues on down the chain. And in the book, again, has a more general argument for it. But we know, thanks to that argument and extending the one I've made here, that each basis vector that we add, V1 through V3, spans the same space as X1 through X3, or as we see down below, the span of V1 through VK equals the span of X1 through XK for any step up to P, right? For any of our vectors 1 through P. So that's a nice piece of information to have, as well as this process for generating this orthogonal basis. Now, we know that each subsequent vector in this process is perpendicular to the one before, or orthogonal to the vectors before it. It's not so prudent to come in here and try to take a dot product of the kth and jth elements, VK and VJ, because those are general inner products that you'd have to calculate. Might be a little bit harder to see. It's probably best to look at it in this light. We know that V2 is perpendicular to V1 by construction, right? It's the projection of X2, or it's the projection of X2 onto V1, and we subtract that from X2. So we get rid of the component of X2 that's actually in the space spanned by X1, and we only keep the component that's orthogonal. That's this whole difference right here. So these are Z's from the previous problem. We're keeping only the Z components, the orthogonal components, and we do that at every step of the way. When we come up with a third one, this is like when we found the third vector in the previous example. We found the projection. It was the sum of these two projections here. And this is a projection of X3 onto the space spanned by V1 and V2. Note that it's V1 and V2 and not X1 and X2, right? We have to be perpendicular to the space that we're building, V1 and V2, as we build these orthogonal vectors. So be sure to keep that in mind as you work on these. But, and then we find the component of X3 that is in this space spanned by V1 and V2, and then we subtract it from X3 to sort of get that component out and just leave us with the orthogonal component of X3 to the space spanned by V1 and V2. And that becomes our V3 vector. And we continue that down the line until we get to VP to match the same number of vectors, basis vectors we started with, and we'll have an orthogonal set of an orthogonal basis for W. And not only that, we'll know that for any list 1 through K, on our way up to 1 through P, we'll have the same subspaces spanned by these vectors. So that's the Gram-Schmidt process. Now, let me show you where we want to be careful to use V1 and V2. So in the previous problem, let's look at when we calculated the third vector. I know this is U1, but remember we also chose it as V1, right? It's the first one that we get for free. It's the only one that will always match the first vector in our original basis. Now, U2, or so when we go to for V2, I didn't use U2 here, right? I did for my second vector in this projection onto the subspace S. I didn't use U2 here. I picked up this vector that I previously generated. This is my Z1 vector, right? This is, or which really is V2 if we think about it in terms of the next theorem on the next page. And I used that vector in this formula. And subsequently, if we had a fourth vector that we needed to generate, so this was a basis with 4 vectors in it that were linearly independent, of course, and we needed a fourth orthogonal vector, I would use these 3 vectors as V1, V2, and V3 in the formula, and V4 would be generated from X4 and these 3 vectors, X4's projection onto these 3. I would not use U2 and U3 where these 2 would fit into that. And that's a distinct thing to keep in mind when you're looking at this formula. It's not X1 and X2 here, it's V1 and V2. Because remember, when we build a new vector, V3, it's got to be perpendicular, or we're trying to subtract from it its projections onto the set of vectors, or the space spanned by the set of vectors previous to it. So that's one note of caution there. So another example asks us to construct an orthonormal basis for the vectors of example 1. Well, we actually accidentally already did that. But in the case that we hadn't, right, if we took our basis from example 1, which we already found, and we normalized, then, well, just to check, we could normalize these once again, right? So here's us writing this as a normalized or orthonormal basis. We've taken the length of this vector, we're dividing by this vector by that length. Same thing for this vector, we're dividing by its length. And what we end up with is exactly what we had because we already converted it to an orthonormal basis. I believe there's some kind of typo in these notes when they were put together, but nonetheless, it's still a decent demonstration of converting an orthogonal basis to an orthonormal basis. Remember, orthogonal just means that the inner product of any pair of vectors is 0, distinct vectors, that is. And then, well, then the inner product of a vector, any vector in this list with itself, is 1. And we could check that that's the case for what we have here. So that's the orthonormal basis situation. Now let's apply this Gram-Schmidt idea and theorem to QR factorization of a matrix. We're going to use this QR factorization of a matrix in order to come up with a solution to, or at least a convenient way to solve, the least squares problems that we're going to see in section 6.5. So if A is an m by n matrix with linearly independent columns, then A can be factored as A equals Q times R. So think about it like this. If A has linearly independent columns, it has n columns. So we can think of this as, this is a basis for the column space of A. So if we think of those vectors as a basis for the column space of A, well, then we can come up with an orthonormal basis, or at least an orthogonal basis for the columns of A. For that, remember the column space of A is a subspace of Rn. So, or Rm rather, but we could, since we have linearly independent columns, are just like having, n linearly independent vectors. So we can come up with an orthogonal basis based on those linearly independent vectors. So, and that's really what this factorization is about. It's the sort of the matrix version of Gram-Schmidt. And we're going to see this finished off in just a moment. So it factors into A equals QR, where Q is an m by n matrix whose columns form an orthonormal basis for the column space of A. That's exactly what I was just talking through there, right? The orthonormal basis, well, those are the Gram-Schmidt vectors based on the column vectors of A. And then R, a little bit sort of outside the idea of our Gram-Schmidt process, R is an n by n upper triangular invertible matrix with positive entries on its diagonal. Okay, so the intuition for this is to look at A as its columns, x1 through xn. It has n columns, they're all linearly independent. So we can form, and these form a basis for the column space of A. So this is the subspace W from the Gram-Schmidt process. We use the Gram-Schmidt process to yield an orthonormal basis, U1 through UN, for the column space of A, right? We just run it through that algorithm of the previous theorem. And then we let Q, this new matrix, be equal to that, the matrix of orthonormal vectors as columns. So U1 through UN is the orthonormal basis for the column space of A. We let Q be this matrix of these orthonormal vectors, U1 through UN. Okay, so now we just note the following. For any K, 1 through N, we know that XK is in the span of U1 through UK, right? We've taken pains really in the examples so far to talk about the fact that XK is in the span of U1 through UK. Note that it's not all n of these vectors, right? It's not all n of the UN. We can generate XK by simply U1 through UK, right? And this is that sort of last line of the Gram-Schmidt theorem. We'll look at that real quick down here, right? We know that XK is an element of the span of V1 through VK. In our case, U1 through UK. So now, since that's the case, that means that xk can be written as a linear combination of V1 through Vk. And that's what we'll do. And we'll let this R be these constants R. So since xk is in this span, there exist constants R1k through RKK, right? So 1 through k, so there are k constants R1k through RKK, such that xk, that column vector, is equal to this linear combination R1k U1 up to RKK UK, and then anything after that is just zeros times all of our basis vectors that are past the kth basis vector in our orthonormal basis up through the nth basis vector in that basis. Now, imagine this. If we were talking about x1, then x1 is in the span of U1. So there exists constants, well, just a constant, R11 would be this constant here, and x1 would be equal to R11 times U1. So everything else would be zeros. So we'd have this vector of constants or scalars, R's, where there'd be 1, and then every other scalar under that, with all these weights would be 0 afterwards. So when we're talking about the kth element, we have non-zero values until we get to the kth element, and we have zeros after that. So if this was x1, then R1 here, this vector, would be 1 right here, or just R11 right here, and then zeros for everything below it. For the second one, it would be R1k, R2k, and then zeros below that. And so for the kth one, as we see, it's R1k through RKK, and then zeros below that. Now, that's clearly, as we go from R1, which has 1 non-zero and zeros, and then R2k, which has 2 non-zeros and zeros, if we stack up those columns, those R's, as our columns in a matrix capital R, well, then we're going to form an upper triangular matrix, because this will have zeros after it's underneath its first entry, all the way to the nth column, which has non-zeros all the way down. So that's a triangular matrix. And moreover, what we see is that A being equal to x1 through xn, well, Q times R, remember this is U1. So remember that a product Q and R is written as, these are the rows or the columns of R, Q times each column of R, right, for a matrix multiplication. So we see, and then each Q times R1 is really, this is the linear combination of Q, U1 through UN, with the vector R1 as weights. R1 has only one R11 right here, so it's R11 times the first column of Q, which is U1. And that's how we get X1. And then so on and so forth. Each of our XKs along this line up to XN are equal to each of these QRNs. So we see that we have this matrix decomposition, A equals QR for these two matrices. Now, why are the diagonal elements of R are positive? And that's a detail that's handled by the proof in the textbook. So this proof gives us, to some degree, an algorithm it's a constructive proof to some degree, because it shows in the proof, it shows us how to construct such matrices Q and R that are a decomposition of A. So the first one, well, it's really implied by the theorem. Q is just an orthonormal basis for the columns x1 through xn of A. So that's how we'll construct that one. And then for R, well, a key thing to note about R is that Q is a matrix with orthonormal columns. So Q transpose times Q is the identity matrix. So Q transpose times A and Q transpose times this side leaves us with Q transpose A equals R. So that's how we'll find R, and we'll do that in the next example below. So find a QR factorization of the matrix A. We have a 4 by 3 matrix here, and so we want to find Q first. Well, we've already worked with these columns as vectors and a subspace, so that's nice. We already have an orthogonal basis for these vectors, and that was as follows here. We just did this in a previous example. So an orthonormal basis for this would be to normalize all of these, or each of these 3 vectors. So once we do that, divide each vector by its length, we have these 3 vectors. It's the result. So that's a little bit of work, but it's nothing conceptually difficult. So this is an orthonormal basis of the column space of A. It's exactly what that matrix Q in the theorem needs to be. Q is an m by m matrix. It's an orthonormal basis for the column space of A. So we've got Q handled, right? This is our matrix Q. So as I argued before, to find R, we note that Q has orthonormal columns. So Q transpose Q is equal to the identity matrix. Now, if we're sure that we've calculated this orthonormal basis correctly, then we could just trust that this is the case. And we don't have to carry out that multiplication of Q transpose times Q to make sure we get the, I think it'll be a 3 by 3, yeah, it'll be a 3 by 3 identity matrix. If you want to check 1 or 2 rows and columns, then perhaps you could do that. But we know, so long as we built this thing correctly, that this is going to hold. Now, remember, what does this do? Well, A equals QR is what we want R to satisfy, right? We want R to be a matrix that satisfies this. We know A and we know Q, and we know that Q has this property. So let's use that. So A equals QR, Q transpose multiplied on both sides of this equation, looks like this. Q transpose times Q is the identity matrix. So Q transpose A is the identity matrix times R, which is just R. So in order to find R, we just write it as Q transpose times A. We already know Q and we know A. We can easily find Q transpose and carry out this product. And when we do, we arrive at this 3 by 3 matrix right here. Notice that it's upper triangular and it has positive elements along its main diagonal. So our decomposition of A as Q times R is as follows. This is A, it's equal to our matrix Q times this matrix R that we just found right here. And that's our decomposition for the matrix A as a QR factorization, is what it's called. Now, matrix factorizations come in all types, all different types. Oftentimes, you're interested in a matrix factorization to simplify computation. In a lot of cases, that'll be applied in a numerical situation where you want to simplify computation numerically. You might be having a computer. You might have a computer calculating something for you algebraically that one of these factorizations can be very handy for. But again, all we're going to look at it for is to find a solution to the least squares problem. So that's our main purpose for this, and that'll be our sort of capstone section of all of this material.